Welcome to The Explainer. Today, we're diving into a paper that really changed the game for computer vision models, all by asking one simple but powerful question.
And that question right there is the whole idea behind the Squeeze-and-Excitation Networks paper. It was a breakthrough that gave AI a new way to focus its own attention. All right, let's get into it.
So here's our roadmap. We're going to start by setting the scene, what computer vision looked like before this paper. Then we'll unpack the brilliant core idea, check out the pretty stunning results, and finally, we'll explore the huge impact it's had on AI ever since.
To really get why this paper was such a big deal, we need to kind of hop in a time machine and go back to around 2017.
Back then, pretty much everyone was obsessed with one thing: architecture. The whole game was about making networks either deeper, like VGGNet and ResNet, or wider, like the Inception models. It was all about trying to capture spatial information, the shapes and textures in a picture, by just piling on more and more layers.
But while the entire field was laser-focused on going deeper and wider, the authors of this paper decided to look somewhere else entirely. They looked at a part of the network that, honestly, most people were overlooking: the relationships between its internal channels.
They decided to focus on these feature channels. Now, you can think of each channel as its own little feature detector. One might be looking for vertical lines, another for the color blue, and maybe another one for a furry texture. The big idea was, what if you could teach the network not just what to see, but which of these detectors were the most important for figuring out the image?
And what they came up with was this super elegant and honestly surprisingly simple little building block that they called the Squeeze-and-Excitation block, or, just the SE block for short.
Okay, to really get this, think about it like this. A regular network is kind of like a soundboard, where all the volume faders are just stuck at the same level. It treats all its features pretty much equally. But the SE block, that's your expert sound engineer, who listens to the whole mix and then intelligently decides which instruments to turn up and which to turn down.
And it does this in two dead simple steps. First, the squeeze step. It takes a big picture look at every single channel and basically boils all that information down to just one number, the gist of that channel. Then, the excite step uses that summary to calculate an important score for every channel, deciding which ones need to be amplified.
The real genius here is just how simple it is. The SE block isn't some brand new, crazy complicated network. Nope. It's this tiny, lightweight little module that you can just drop right into architectures that already exist, like ResNet. It just hangs out at the end of a block, looks at the output, and fine-tunes it before passing it along. It just makes the old network smarter.
Okay, so it's a cool idea, but the million-dollar question is, does it actually work? Well, let me tell you, the results were, frankly, spectacular. This number you're looking at, 2.251%, that's the top 5 error rate their model got on the huge ImageNet dataset. And that number, that won them first place in the ILSVRC 2017 competition. And it didn't just win, it absolutely smashed the previous year's winner by about a 25% relative improvement.
This table from the paper really lays it all out. Just look at the SE ResNet 50. For a tiny, almost unnoticeable increase in computational cost, we're talking just 0.26%, it blew the regular ResNet 50 out of the water. In fact, it got so good that it started creeping up on the performance of ResNet 101, which is a network that's twice as deep and way more expensive to run.
But look, the impact of this paper goes way, way beyond winning one competition. This thing helped kickstart a whole revolution in how we actually think about building AI.
This quote from the authors really gets to the heart of it. They gave networks a way to perform feature recalibration, or in plain English, a way to learn what to pay attention to all by itself.
And this idea, this concept of self-attention, man, it is everywhere now. It's a cornerstone of so many of the most advanced AI systems we have. We're talking about the models that generate mind-blowing images, the huge language models you probably talk to every day. You can trace a direct line from them all the way back to this paper.
The Squeeze-and-Excitation Network was just a monumental leap forward. It made AI more efficient, more powerful, and a whole lot smarter. It really taught networks how to focus, which leaves us with the really exciting question of what we should focus on next.
And just a final note, this is for entertainment purposes only.